Hi, I'm ready to begin. Thanks. Okay, let's get started. I hope you had a good and refreshing spring break. Welcome back. I'm sorry it's not so great today. It doesn't look so promising this week. Let's see. We had the that's not what I meant to do. The midterm assessments. And thank you, many of you. I had pretty good response rate. Is that going to work? So thanks for taking time to do that. There's kind of a mixture of responses to the class. If you hold on, see if we can look at them. What's this? No, it's not it. Okay, sorry. I closed the window accidentally there. Overall quality. Most people like it, but some people don't like it at all. So I'm getting the top 4 and 5s, I'm getting 6 and 7, and then 1, 2, 3, I'm getting 1, 2, 1. So, I don't know, I guess I'm doing stuff which some people like, but some people are not so keen on how it's going. The comments I got, the main thing is somebody would like me to spend more time on the lectures and less time on the practicals, and some people said that I'd like to spend more time on the practicals, which, I understand. I would also like to spend more time on the lectures and more time on the practicals, I guess. So that's just the problem of the amount and the range of stuff I'm trying to cover. So I think the comment about the lectures is they're kind of superficial, and that's definitely true, because, given the choice between covering one thing thoroughly and and surveying everything that's out there, it's my goal has been to just let's touch everything that's out there, and then if there is something you want to know about, at least it's there and you can go and find out about it later. But the downside of that is that, I tell you about these things, but I just tell you sort of the top level and not enough for you to go off and build it by yourself. But that's the compromise I've chosen. And to some extent, the practicals are meant to remedy that a little bit. I don't teach you how to do it exactly, but I show you a thing that's doing it. And so that's a good place to start if you want to figure out how to do it yourself. So yeah, there are compromises in this kind of stuff. But the choice of mentioning things without necessarily explaining them in depth is, I guess it's a slightly unusual one for this kind of class, but at the same time, I'm interested in just trying it out, seeing if we can still make it worthwhile. But I am open to suggestions. So if you have any further ideas that you think we can improve it, then please let me know, or talk to Byung-Suk. Okay. Any comments or questions? In terms of the course outline, so we just finished spring break. We have 6 regular weeks left of lectures and practicals. This week we're talking about time and pitch scaling. Then we're going to do beat tracking, chroma features and chord recognition, alignment and cover songs, music fingerprinting, and then some stuff on source separation at the very end. So this is kind of moving, the earlier stuff was more about the low-level music. We start off with music synthesis, then we had kind of music processing, like studio type effects, and now we're moving into music analysis, the kinds of sort of getting information out of music audio, which is the focus of the music work in my lab. So hopefully this will be interesting too. And we'll be moving away from real-time stuff and more into offline MATLAB-style analysis. Okay, any... Okay. All right, let's get going then. So, last time we were talking about pitch tracking, which is this idea that we have signals with a particular period, which is very important perceptually in the quality of the sound. And now today we're going to talk about pitch scaling, which is the idea of modifying the pitch of a piece of sound or a piece of music. But the challenge being, how do you modify it without at the same time change, or how can you modify its pitch without changing its timing, or vice versa? I'm just going to make sure the sound is working here. Sound is not working. Oh, that's all right. It's not. That's always a good place to start, because the power cable is not plugged in. One of these ways up. Okay, got it. Okay. Yeah. All right. All right. Okay. So, it's easy to think about this problem, right? We hear a piece of sound, and it's got a sort of a perceived evolution in time. It develops, it changes through time at a certain rate. And so you can say, well, I'd like it to be faster or slower than that. How can I achieve that? And, well, there must be a way to do it. So one obvious thing to do is just to change the sampling rate, or equivalently in analog terms to change the speed of the tape that you're playing on a tape recorder, something like that. Just take the waveform and stretch it out or compress it in time so it actually just occupies more or less time. So if we wanted to make something, and so mathematically we could just say, well, we're going to take the waveform, but we're going to dilate it in time, so the time that did occur at time t now occurs at time rt or something like that. If we do that for a piece of speech, it sounds like this. So that is the classic sound of slowing down, a tape recording. And it's slow, right? I mean, the speech sound is slow, and it took twice as long to play as the original speech sample. But it didn't sound like natural speech. It didn't even sound like someone speaking unnaturally slowly. It sounded like this weird grumble sound. And that's because when we do it, we slow it down in time, but we also compress it in spectrum. That's the thing that happens. So now that's the problem. We want to slow it down in time without compressing the spectrum. We want to keep the spectrum at the same range of frequencies. That is, if we had a single sine tone, 1,000 hertz, lasting a second, sampled at 16 kilohertz. If we played it out at 8 kilohertz, it would now last 2 seconds. But instead of being 1,000 hertz, it would be 500 hertz, because there are exactly 1,000 cycles in that waveform. If we stretch them out over 2 seconds, now there are only 500 in each second, so the frequency is halved. So one thing we want to, the most obvious thing to do is to try and change the speed, the duration, the time scale without modifying the frequency. But the other thing, the converse of that also has applications, that we want to keep the duration the same, but maybe we want to change the frequency. So this might be obviously for musical applications where we want to change the pitch, because the pitch, even a small amount of pitch change can have an important musical effect. But the timing has to be maintained because it's in rhythm or something like that. Turns out we can always do this. If we can do this, we can always do this. Because if we just change the duration to be like 10% different, and then do the thing of speeding up the tape or slowing down the tape to make the duration the same, then now when we change the sampling rate, the tape speed, the frequency will shift. So if we can do this part, we can do this, or vice versa. They're the same modulo this sampling rate thing. But the difficult part is changing one without changing the other. So this is a long-standing problem, and this is the detail of a tape player or a tape machine that did this from the 1950s. And what it did, you can't really see what's going on that well here, but the tape comes in here, goes around some capstans, goes into this thing, which is this box. You can't see what's inside, and comes out and goes back to the tape reel. And if it was just a regular head in here, a regular tape head, it would just be a regular tape player. But instead, what's in here is this rotating head. So I don't know how they did this in the 50s, but there you go. The tape goes wraps around this head, but the head itself is spinning, and actually has four. So a way a tape works is it has a piece of metal with a little gap in it, and then coils wrapped around the metal, and then the magnetic material in the tape near the gap depends on how strong it is or what orientation it is. It'll induce a different amount of voltage into that gap. So it has four actual tape heads, four different reading places, and then as it spins around, the tape is moving, right? Because the tape is just being fed in off the spool and coming back out again. And it's the relative motion of the tape and the gap that induces the voltage that gets picked up. But in addition to tape moving, the head is also spinning. So there's kind of combined motion of the head moving and the tape moving, or the relative motion of them. And then because the tape is wrapped around a quarter of the head, as one of these heads sort of ceases to be in contact with the tape, the next one comes in. But what this means is that, if the head was fixed and it was just looking at this little chunk of the tape, then that would be reading the waveform off and getting the right thing. But now the head is moving, so it's seeing a different part of the chunk of the tape every time, and then as one head disconnects, the next one comes in. So it's sort of basically, at this point here, head A is about to disconnect, and then head B will suddenly start connecting and start reading the waveform. So this little chunk of tape is going to be read almost twice, depending on how fast this head spins. It already got read once by A, then it's going to get read again by B, except the fact that it's moved on a little bit. And so what this does, this spinning head, basically, and then the output is the sum of all these different head outputs, but it's only one at a time that's in contact. So the spinning head is sort of reading the same little chunk of tape over and over again, except it's lapping, it's moving forward slowly as the tape moves forward. If you keep the tape moving at a steady speed, then the speed of the head relative to the tape is faster than if the head was stationary. So it's actually reading the waveform back at a higher rate, speeding up the waveform. So it's shifting up the pitch even though the tape is going through at normal speed. So that would be moving the frequency without changing the time base. If you slow the tape down, but then have the head spinning such that the actual rate of motion of the head relative to the tape is what it should be, but now the tape is moving slower than it would normally, then you're preserving the frequency because you've got the right local structure of the head relative to the tape. The local waveform is the right shape, but the global timescale is being slowed down because the actual tape is moving more slowly. So that's the basic principle. But this is how you do it mechanically, which is kind of tough thing, but there you go.
Yeah. Not know this, but do you need a stronger, like acetate type tape if you're actually rotating the head? Isn't that more abrasive?
No, so I don't think so. Even in the conventional tape recorder, the tape is sliding over the head, right? That's what you need to make it happen. Now, it's a big problem in making, it's a big challenge in the manufacture of this tape to make it so it doesn't, wear off the head and doesn't break and stuff. So, but it's not significantly different here, particularly in the scenario where you're making the sound last twice as long, but keeping the frequency the same. The actual rate that the tape is sliding over the head is the same as it would be in conventional recording. And in a regular tape recorder, you can sort of fast forward it, and on a reel-to-reel, you can keep the head in contact, and you can hear it sort of sped up. So that's not a problem. Making this head that rotates. So the thing that I don't know how they did was you have to have a rotating head, but you have to take the voltage out of it into circuitry, and then it's like it's microvolts or something. So they have to have these kind of brushes to get the stuff off, which is these things are super sensitive magnetic things. So I don't know how you spin it without getting interference, but anyway, that was the engineering challenge. Okay, so that's how you do it in analog. In the computer, of course, it's much easier. But we can think about doing exactly the same thing. We could write it down mathematically like this. Y is our output, and we have windows in the output. We index them by m. So the mth window occurs at m times L, where L is our sort of hop size between successive windows, and then with some samples within that offset. And so the output after the mth window is the output after the m minus 1th window. So we take the previous thing over the same range of samples. So some of these won't have been touched yet, so they'll still be 0. And then we add on something from x. X also offset by n, indexed by n, where n is our particular window. But now instead of starting from ml, we're starting on the floor of m divided by r, where r is our scaling factor times l. So it's some other window of x that we take, and then we have a little tapered window here to make sure we don't get hard edges. So all we're saying is that here's our original x. We chop it up into a set of individual pieces. We apply some tapered window here. So we've got these 6 individual windowed pieces like this, and they're overlapped. So we sort of see, here they are, but this is them on their original timescale. And then, for instance, to spread it out by a factor of 2, we just play each one twice. So the first one goes down here, and then it goes down here where, at the timing that was where the second one originally came from. And then we have the second one, we put it down twice, the third one, etc. So now this original set of 6 windows lasts this much longer. And if we look at the waveform, this is actually the waveform you get if you do this. You can see that here we've got these, whatever they are, pitch pulses. And here we've got basically the same structure of the pitch pulses, but now it's lasting twice as long. And then the gap here has been delayed in time. And then these pitch pulses come in later. So when you sort of draw it out this way, it's pretty obvious what's going on. When you think about it in terms of what the tape machine was doing, and this is the tape machine running at half speed, and each head seeing the same chunk of tape twice. So it's not exactly the same. I guess the tape machine would actually have a kind of an extra window in here, which was 1.5 you'd put in here, which would actually be a nice way to do it. But it's pretty close to that. And this is what it sounds like.
Football team coach has to watch 10 minutes at a time.
Okay, so now we can recognize the speech. The frequencies of the actual pitch and the formants are actually the same. They're the right ones, and it lasts long, where it's been slowed down in time. But it doesn't sound that great. It sounds like it's got this kind of weird metallic thing going on. And what we're hearing is actually these individual windows. That these windows are now they're not at all synchronized with the speech signal, and so there is some element of modulation in the spectrum in the signal that's occurring at the rate of these windows, and that's what we're hearing. Yeah. WN is the red triangle here. It's it's the tapered window. It's the time localizing window. So, and that's basically what the mechanical machine would have sounded like as well. I mean, it depends. The frequency or the frequencies of the artifact depend on the length of the window. But you can't, they don't get any better, significantly better, I don't think. So I think that's, that particular tape machine was probably okay if you wanted to slow things down, if you were just trying to figure out what was going on, but it wasn't like pleasurable listening. So one way we can explain the problem is that we're doing this overlap adding, and the overlap adding of these little triangular pieces, that's important in terms of, avoiding artifacts. If we just use rectangular windows or we didn't have any overlap, we'd sort of get these discontinuities at the edges of the window. So we need the sloped parts. But in the overlap region, we're getting kind of arbitrary bits of waveform falling on top of each other. And so we can either get constructive or destructive interference in those parts because there's kind of this uncontrolled phase interaction that's occurring during these overlap regions. So, okay, well maybe we don't have to put them down arbitrarily. Why don't we, for each individual window that we're trying to put down, say, all right, this is where we want to put it, but I'll allow myself a little bit of wiggle room here. I'll try putting it maybe a little bit early or a little bit late and see if I can find some point within that region where it lines up well with the existing thing. And so how do we decide if it lines up well? We can just look at the correlation. So here's the rule. It's the same thing for the mth, for this mth iteration of the mth window and the output. We take the m-1th window, we add in some x, but now we just have this one extra term, km, which is an offset specific to the mth window, which is going to try and optimize the alignment of that little chunk that we're adding in. And here's how we choose it. Km is the offset that maximizes over some window the correlation between the waveform we had so far and the bit we're adding on, right? So that we just basically look at the correlation between these two, and then we move them around until we get a local, we get the largest value in the correlation, normalized by the energy, so it's a normalized correlation, and then over the acceptable range. So we have some limited window that we can move things over, but within that window we find the point that lines up the phase, and if we listen to that.
Football team coach has a watch and there's a dime.
We've gotten rid of the frame rate artifacts, and in the regions of like sustained vowels, it actually sounds very good. You can't really hear any boundaries at all. During the transients, there's a little bit of weird kind of stuttering or echo, and what's happening there is that it's putting down these windows, but the windows have some single transient in, so there's no really getting around it. It doesn't line up. It tries to line up against itself, and then that moves out of the window, and so then it has to put another one down. So it gets some sort of repeating transients, but for steady state or smoothly changing sounds, it works very well. And it's pretty cheap. It's not difficult to compute this. So that's called SOLAFs, for synchronous overlap add with fixed synthesis or something. But there are various ways you can do this. So there's this interesting. It turns out that the problem that we started off with, of trying to take a piece of sound and stretch it out in time, is not actually that well defined. There's nothing really wrong with the first thing we did, which was just slowing it down in time. Like we took a piece of sound and stretched it out. And you say, oh, but I want to preserve the frequency content. And it's like, well, you can't, arbitrarily preserve the frequency content. Basically, what you have to do is you have to define some boundary between what you consider time content and what you consider frequency content. Which is the same thing we saw in making the spectrogram. You have to choose what the short time window is in order to get the particular spectrogram you want. And it's not that hard to do it, because it turns out that there are numbers that make sense perceptually for us, but that's just that. Now you have to recognize that we're imposing something about our own perception on that. So it's the same with this, that the particular effect that you get depends very much on the time window you use. That's how long that little triangular thing that we're using to pull out each little part. Because within each one of those windows, that's our sort of unit of local time structure. Because we're just copying those things down, whatever happens within that window is going to stay the same. But any structure that occurs beyond that window that takes longer than whatever it is, that 25 milliseconds to evolve, that's the part that's going to get stretched out or repeated. So as the window gets shorter, we're preserving local structure only on a shorter and shorter time scale. And so at some point in particular, the pitch pulses are going to start falling outside of these windows, and then we're no longer going to be able to we're no longer going to maintain the pitch. So here's an example with a normal window, 25 milliseconds. So 25 milliseconds is long enough to capture several cycles of, say, 100 hertz male voice pitch of 10 milliseconds. And so typically we get the pitch cycle preserved.
Football team coach has a watch, then is the dime.
Okay, so that's the same, similar to what we heard before. Now, if we make the window much shorter, 5 milliseconds, that's not long enough to get the whole of a 10 millisecond pitch cycle in it. So now, what happens is this.
Football team coach has a watch, then is the dime.
So it's still fully intelligible, which means that the formants are still in the right place, right? That all the vowels and stuff are being properly rendered. But what's happened is here you can see the pitch pulses are all nice at the same spacing as they were in the original. But here, the pitch pulses are not being preserved. They're actually getting, not only are they being stretched out, but they're sort of being irregularly placed because you've got these short windows. One short window has a pitch pulse here and the next one doesn't. They repeat, but it's not clear whether they don't know whether they've had a previous pitch pulse or not. And so what we end up with is voice where the pitch has been lowered because the pitch pulses are being stretched apart, but also the pitch pulses are kind of irregular, so it has this kind of creaky, dysarthric speech kind of sound. But again, there's nothing. This is not really worse. It's mathematically the same. It's just a different parameter. But perceptually, they're very different because it turns out that what we mean by preserving the time structure is very specific to the kind of signal that we're dealing with. One refinement of this is to think about the source filter model. We said that we can often regard speech as an excitation, for instance, coming from the vocal folds, going through this filter, for instance, the vocal tract. If we decompose the speech into that kind of representation, the filter, the whole point about doing this was that the filter, the vocal tract, is relatively slowly changing, right? It depends on the position of your tongue and stuff like that, things that are mechanical that can't move that fast. And so, for telephony, this is a good thing to do because this has a relatively low data rate. You can downsample it, and it doesn't suffer much. But that means that you can, if you want to do time scaling, you can also do it in this domain. So you break it down, you take the filter coefficients, and you just stretch those out in time. Again, they're slowly changing, they're smooth, so you can stretch them out. The residual is the part you have to worry about. But now we've just looked at a few ways of doing that, so we can use some kind of timescale modification technique on the residual. This is going to introduce some artifacts, but things like the transient pulses getting repeated or something like this. But then we can reapply this nice smooth filter onto that, and so that can actually help hide some of the artifacts. So in fact, it's less important what we do in here because we're going to reimpose this nice voice-like shape onto it. And so that's an idea that turns up a few places. There's this very high-quality timescale modification system by Hideki Kawahara, which is used a lot in modifying speech for psychoacoustic tests. You want to systematically change something like the pitch of speech, but you want it to sound natural so that people aren't distracted by the transients. And that's what his system is good for. So if we do that, we get something that sounds like this.
Football team coach has a watch and a sedan.
There's some, it sounds different, and there are some artifacts, I think, in there from what happens when I slow down the frame rate a lot, but it has a different sound, yeah.
So most of the excitation you usually use is the white noise excitation or other excitation?
In this case, this is what I'm doing. I'm taking the residual, right? If I just taken this filter and this residual and put the residual back into the filter, I would have got something which was more or less exactly what I started with. But now I'm slowing down the filter, and then I'm getting a new residual, and doing that by doing my time scaling. So my SOLAFs or something on the residual. And so, you know, when we looked at LPC, if you listen to the residual, it's like this very, very buzzy. You just got the pitch in it. If I slow that down and I do it in, you know, one of these nice pitch preserving ways, I get this new residual which is still full band and it's still got the pitch, but now it's moving more slowly. But then I reimpose the filter separately. Yeah.
How do we scale it?
Oh, so the filter, what is it? The way we do this in LPC, right, is we take the filter and then we say, okay, I'm going to have a new filter every, 20 milliseconds. So we basically take 20 milliseconds of excitation, a fixed filter, run it through, and then we take the next filter and then do the next thing, etc. So now I can just do these frames twice as long, 40 milliseconds. That doesn't really get me that much. What I can do is actually interpolate. So I've got these two filters, for time 1 and time 2. I can regenerate a new filter which is sort of midway in between. Now that raises the question, how do you do that? You don't do it by taking the average of the filters, because that would not work well. But what you can do is you can take like a pole zero representation and try and find the continuity between particular poles, and then sort of take the poles halfway in between, something like that. Normally it's easier in other domains like the reflection coefficients. If you have a reflection coefficient filter, you can average those things without worrying about getting an unstable filter. And so that's often how it's done. It's common in speech coding to do that. Actually, I don't know how I did it for that example. I don't remember. I probably just did double, repeated each frame twice. Okay, so that's doing it in the time domain, so thinking more or less about the signal as little chunks, and it's very efficient, and it often works pretty well. But it's sometimes easier to think about what we're trying to do in the spectrogram domain, and that leads to a timescale modification algorithm called the phase vocoder. So the idea here is, if I plot a spectrogram of a piece of sound, and I say, well, I want to stretch it out in time while preserving the spectral structure. Well, I can see exactly what that means now. The spectral structure just means I want to have these dark ridges and this detail here stay at the same frequencies. But stretching it out in time just means like I want to make it twice as long in this dimension. And so simply by, as it were, replotting this spectrogram on a different time axis, I've got the image of what I want to get out. And so it's like, well, that's it. I just want to, whatever sound this corresponds to, that's what I want as my output. That would be fine, except, of course, we don't actually resynthesize directly from the spectrogram image. What we resynthesize from is the magnitudes and the phases of every short time Fourier transform bin. And we don't plot the phases here, but they're there. Here, we can stretch it out in time, but we don't have we still don't have the phases shown. It turns out if we use the original phases, we're not fixing it. That would just be the same as repeating every short window. So we know what it looks like in the spectrogram, but we don't directly have the waveform that we can listen to yet. There are a bunch of different situations where people would want to modify a spectrogram and then regenerate the sound. For instance, you might have a spectrogram where you can see a particular sound source, and you want to get rid of that sound source, so you could just like zero out those parts of the spectrogram. Or you might want to move something around in time or frequency. And so it turns out there are several applications where you'd like to be able to go from a spectrogram, just the image, just the short-time Fourier transform magnitude, and resynthesize a time waveform. So there are a bunch of approaches to this, and one of the most well-known ones is this Griffin and Lim algorithm from 1984, which is basically iterative. You start off, we have the magnitude, but in order to do the full inverse short-time Fourier transform, we need the phase, we need the angle. So you start off with some guess around the phase, some arbitrary, at random or whatever you want. You do the resynthesis there, which involves overlap adding, inverting every frame and then adding it on. And that gives you a full time domain waveform. And then you do the forward for a short-time Fourier transform again to get the same frames out. Now, in general, because of the uncoordinated phase interactions between the successive windows, the magnitude of this new thing, will not be the one you started off with. There'll be some distortion to that magnitude. Okay, but you throw away the magnitude, you just keep the phase of that thing, because now the phase of this thing is going to have whatever magical structure there is between the phase of successive windows that comes from a real signal. So you keep the phase of this, and then you just plug it in here. You take the magnitude that you want, you take your now slightly improved phase, and you then reconstruct, and then you reanalyze again. That gives you another new phase function. You reimpose the correct magnitude, etc. And this converges. It turns out that this does always improve, but it's very slow. So this is a figure from a paper where we're doing this scheme on some particular data. And you can see that this is two different initialization points, which, this was like random phase, and this was we were trying to show that we could do better than starting at random phase. But you can see that the error, the amount of distortion here, or the signal-to-noise ratio, is growing slowly. So the noise is reducing, but it's going to take a long time, and often you have to do tens or hundreds of iterations to get a good result here. There's some more recent work which actually it has a better way of finding this initialization, but basically this is kind of a painful way of doing it. Even with today's computers, it's kind of difficult to get real-time results here. But of course, we don't have to, at least for the case of time scaling, we don't have no information on what the phase should be. We do still have the original phase. It's just that if we use it directly, then we get these discontinuities in the successive windows. But where do the discontinuities come from? Well, think about this situation here. Here's a sinusoid, and let's assume that it's a sinusoid that's constant in time and frequency. And then here's one window in blue, and then, typically in the analysis, what we do is then we shift everything over, we take another analysis, another Fourier transform here. And so if we did this for these two windows, in the blue window, we'd have a particular frequency, a particular magnitude, and then a phase, which in this case starts at 0, say. Let's say we're measuring the phase at the beginning of the window. And then the green analysis window, which is the same sinusoid, has the same frequency, the same magnitude when we analyze it, but the phase changes, of course, because now this analysis window is starting that much later into the waveform, so it has a new phase, and actually the phase change between the blue analysis window and the green analysis window is the rate of phase change, the local phase derivative, which is the local frequency, times the length of this window, right? So it's just we can predict what the delta phase is going to be by just having as the frequency times delta time, or conversely, if we just have these two measurements, we can infer the frequency of this sinusoid as the phase change divided by the time change. Now, of course, you could say, well, we already know what the frequency is because it's the bin of a Fourier transform. That's what we're actually measuring. Well, we know roughly where it is, but we don't know exactly where it is. We just know which bin it is. This is a precise measurement of the actual phase change as a phase change in time. Okay, now let's say we're going to resynthesize this little chunk of waveform, but we're going to resynthesize it so that it's twice as long, which means that this green waveform here, when we resynthesize it, is not going to lie at this time, it's going to lie at this later time here. Right? It's going to be shifted later in time, assuming the blue is kind of the origin here. What we'd want to generate is this little chunk of red waveform here. It's got the same frequency and magnitude as the blue and the green, but in order for it to line up correctly with the blue, if we just took the green waveform and put it here, then it would not be lined up with the blue. There would be a phase interference. What we want is this phase here, which will just nicely connect up with the blue. All that means is that whereas before we had this particular phase change here, delta theta, now we want a different phase change here, which is actually just this rate of phase change times the new time step. So it's just delta theta times 2, because it's theta dot times 2 delta t. And if we do that, and if we do that consistently for every bin, for every frequency at every time step, then at least assuming that what we saw in each bin was a single sinusoid like this, we'll be able to reconstruct our frequencies so that the phases will line up. And so that is the idea of the phase vocoder. Basically, you take the spectrogram, you keep the magnitude spectrogram, magnitude short-time Fourier transform. But then you calculate the phase, but you don't keep the phase. What you keep is the phase change between successive frames, which is also the instantaneous frequency in every bin. And then when you resynthesize, you lay down your new points in your spectrogram, your new columns, which have been drawn from some other point, some scaled point in the original spectrogram. And then you look at the phase change that's associated with those particular points in the original spectrogram, and you make sure that you accumulate the phase so the total phase change is preserved. The local instantaneous frequency, local d phi dt, is preserved in the synthesis. And actually, when it comes down to it, particularly for integer factors like this, it actually works out to be very simple. And you can reconstruct your time scale spectrogram with the correct phase without any iteration. So here's an example of our original speech example and stretched out by 2. And this is now, we can see that in the image it looks like this thing stretched out by 2, but this is actually the reanalysis of the resynthesis. So.
Football team coach has a watch and a sedan.
And so that ends up being very kind of smooth and steady evolution of the timescale version. And you can obviously slow it down even further. It sounds quite close to someone speaking very slowly. The only sort of giveaways are some of these consonants where you'd expect it to be very, very abrupt. So this is the football team. Here's the t. The original t is very, t is a little burst of air. And it's pretty abrupt. And here it's just stretched out in such a way that it'd be quite difficult to pronounce with your mouth. But that's kind of, that's the best you could hope for. Well, that's the best you could hope for with a uniform timescale modification. Actually, there's been some work on trying to get even more natural timescaling where you go through and you classify every frame and you decide whether it's a consonant, a transient sound, or whether it's a vowel sound. And then you do the timescaling on the vowels, which are kind of have this nice stationary structure, and you leave the consonants, the transients, unmodified. And that sounds even more like what you get if someone was speaking slower or faster. Of course, as with the time domain approach, this problem still depends on how you define your time window, so your local time structure. So now we can do the same thing. We can stretch out by a factor of 2, but now we can do it with a much shorter time window so that we don't get a whole pitch cycle in time window, which is the analog of taking a wideband spectrogram, a spectrogram with a short time window. And what we can see in the image is now the pitch pulses are being stretched apart. And if we listen to it,
football team coach has a watch and a sedan.
so again, like with the time domain version, the pitch is getting lower. But here, because of this nice, very uniform modification applied in the spectrogram domain, we're actually stretching out each of these pitch pulses so they're exactly twice as far apart. So now it sounds like his formants are in the same places. Right here are the actual formant frequencies, the resonances of the vocal tract, but now they're being excited at half the rate. So it sounds like he's got some terrible sore throat that's making his pitch go really, really low. And again, it's just a question of whether the time structure we want to preserve, whether it falls within a single window of the Fourier analysis that we're using. So the phase vocoder is a fairly old technique. It was proposed in the 60s and implemented digitally in the 70s and became quite popular with computer musicians in the 80s. But it has some problems. I don't know if you could hear it in here, but if you listen to it on headphones, it's got this slightly unnatural sound. It sounds slightly reverberant or sometimes metallic. If you slow it down a lot, it sounds metallic because you get these individual sinusoids which are being stretched out. And it turns out that really what you're assuming is that you're taking each individual bin of the FFT and you're making this assumption about, well, if it was a sinusoid, this would be its frequency and this is the adjustment I'd have to make. So basically you're taking however many bins you've got and in your FFT and treating those as sinusoids. So it amounts to sinusoidal modeling, but without the sort of the full sinusoidal modeling of tracking which frequencies move through time. And sinusoidal modeling in general is more expensive because you do have to have all this extra tracking and computation. But it is a more flexible and more explicit representation. In particular, the places where the phase vocoder fall down is if you've got a particular set of bins, there's some kind of sinusoidal peak here. So we've got this one frequency which is actually at the peak. Then you've got these two flanking frequencies, right? And if you've got, depending on what your analysis window was in your STFT, these are still contributing energy to the central peak. But the phase vocoder says, no, these things are individual sinusoids and tries to make them join up on their own, which doesn't work. Whereas if you actually have a sinusoidal model, it says, no, there's this sort of set of values in the FFT, but there's just one sinusoid here, and that's what we're going to extract, and that's what we're going to model. There were some tricks to try and make that work for the phase vocoder to try and preserve the local phase structure across frequency in the region of a peak. But it's basically easier to just directly try and model as sinusoids. And so we can take our piece of speech, we can run our existing sinusoidal model on that, and we can stretch them out. This one's got a fairly low threshold, which makes it lose a lot of the energy, so we can hear the effect, but then we can listen to what that sounds like.
Full team coach to watch them is done.
So there were some sort of dropouts there because it wasn't picking up all the energy. But again, it sounds very rich and smooth when it gets all the harmonics. It does have this, again, it has this metallic effect, particularly if you slow it down a lot. In a period of noise, the sinusoidal model tries to find sort of these evanescent sinusoids that cover some of the noise energy peaks. And when you slow them down, suddenly they become much more audible as tones, which gives it this kind of weird metallic or glassy sound, which is not really what you want, but that's the consequence of the model. What am I going to say? Okay, that's it. So there is actually some work.
Full team coach to watch them is.
There is some work on trying to, have a mixed model, a sinusoid plus noise model, where you take the energy that you can identify as these sinusoidal peaks, track those, represent them, you can stretch them out. But then there's energy that's left behind, and you fit that with some kind of white noise model or filtered noise model. You estimate the filter, then you have a parametric noise background, and you can stretch that out in time as well, just by stretching out the filter and feeding noise in. Then you can still preserve some of that structure. Okay, any questions about that? Okay, so what we've seen now is in the last lecture, or last time we met, we were looking at pitch tracking, which allows us to extract the current pitch. And then what we've seen now is how we can modify the pitch in some, by some factor. So if we put those two things together, we end up with the ability to modify the pitch in response to what we think it currently is, which is basically auto-tuning, which is, trying to, as it were, fix up the pitch. So that's what we're going to be looking at on the practical on Wednesday. Let me just give you a preview of that. So, auto-tuning, the idea is that you have someone who's singing, and maybe their singing isn't that great. So this is actually, there's a database of query by humming samples where people have just sort of sung into a microphone to try and identify which song they want to hear. And, they're not professional singers, so. Thank you, I turned it off, right. That's not a bad one, but it sounds like amateur singing. So we can take something like that, we can load it in here. And then what we're doing here, we're going to play it back, and we're using Sigmund again, the combined pitch tracker sinusoidal modeler. Here we're pulling out the pitch, but then we're doing some processing here to try and find the nearest integer semitone to that pitch. And here we're pulling out the sinusoids, and then we're feeding it into this patch here, which is just this thing that resynthesizes the sinusoids. But it has this particular input here. The sinusoid thing has been modified so that it has a frequency scaling thing here, so that when you have a particular frequency, it gets modified by the frequency scale before being resynthesized. So it's a frequency scaling sinusoidal oscillator here. And so here we can take the ratio of the actual frequency that we get out of the pitch tracker and the quantized frequency that we get by taking this int operator. And then we can divide them so that we then twist the frequency back the other way, so that the amount that the frequency is over the nearest integer is then divided back out, and so we can quantize the frequency. So let's see what that sounds like. So there, actually, the pitches that we're hearing are quantized. They're not exactly the ones that were maybe the right one on the song, but you can get the effect there that you can actually quantize the pitch, and we can do it also for the Marvin Gaye example, which gives us the kind of something approaching the classic auto-tune sound of turning a smooth pitch contour into a step of like a chromatic scale. So on Wednesday we'll get to play with this, and we can look at some of the ways that why this still doesn't sound like natural, and whether there's things we can do to make it sound more natural. Okay, any questions about this? Yeah.
Just mentioned to find the sinusoid
Sorry, for this?
Like if you wanted to use for this one, like if you wanted to reconstruct the sinusoids, would you use like the linear interpretation?
Yeah. If you wanted to stretch it out in time, then you could just interpolate. However, linear interpolation would be fine. And if you want to stretch it out in frequency, they're discrete values, so that it's natural. It's like at a certain frequency. If I'm going to stretch it out by a factor of 1.5 or 2, then you just move it by that amount. So there's no contour that you have to use. In the mini project, we had this question of the underlying envelope, right? That the sinusoids are a set of discrete, as it were, samples of some frequency shape. But then, if you change the density of the frequencies, what are the amplitudes you should use? And maybe you should use some kind of interpolated shape on that spectrum. In that case, I don't think it matters. It's not that critical what interpolator you use. We're not super sensitive to the difference between, say, a linear interpolation or a sync interpolation, a smooth or a spline interpolation for spectra, for spectral profiles. In time, you can hear the result that the difference between if you take something that's a time envelope, like the magnitude envelope of a sinusoid, and you try and stretch it out, but you use linear interpolation, so you have these discontinuities. You can actually hear that quite often. That you can hear that as a kind of a noise, a modulation noise on the sinusoid, and you're better off using a smooth interpolator. Yeah.
I want to know how do these methods work for music?
Yeah. Okay. So I said, that's a very good point. If we take the phase vocoder and we put a piece of music through it, what kind of results do we get? So I explained that the phase vocoder was essentially working on this assumption that in an individual bin we had a single sinusoid. Because then, if we can measure the phase advance in the sinusoid and we can scale it accordingly. What that means is that works well for a single voice as long as the pitch of that voice is high enough so the harmonics fall in separate STFT bins. If the pitch is too low, then you get something else. We get the stretching out. If you have a mixture of sounds where there are some bins have multiple harmonics falling into them, then you get problems. That suddenly the phase difference you measure between successive bins is actually not something you can simply extrapolate and expect things to stick together. So it typically doesn't work very well. And so the problem of slowing down music is a pretty big challenge. It actually tends to work better in using time domain structure, time domain methods, because at least if I'm taking a little chunk of the waveform, figuring out how to work it out, then whatever different harmonics are present in that waveform, I'm not actually stretching them out. They're all still going to be there. And so if I can find one time alignment which makes most of them line up quite well, then it's going to work out pretty well. Just wondering if I can try that on the fly since we have a few minutes left. So this is my phase vocoder in MATLAB. What we want is to get this little chunk of... let me just see if I can find this grapevine mix. So if I load in a little bit of the actual... Is that working? So that's the mix. Let's get the original as well. So the reason I have I was able to find the multi-track of this, right? Which is why I'm using this example, that I have the actual vocal and I have the mix from the real single release as well. So which is a rare thing to come across, but it's a nice example. So if we use the phase vocoder, we can scale this by a factor of 2. So ys equals p voc ds, and then I want to do it 0.5, and then the time window is going to come from the FFT length. Let's try that. So that's pretty cool, right? You can actually, because you can hear the vibrato and you can hear the kind of the articulation slowed down. But if we try that on the mix, actually, that works pretty good. It's creepy, yeah. Yeah, we can definitely making it faster normally works better because there's sort of more stuff happening, and so the artifacts tend to get lost in the actual detail of the real signal. So yeah, you can easily speed stuff up like this. And then for the mix as well. So later on in the semester, I'll show you. I've been playing around with this, actually using this to timescale videos of like cover songs, so that you can get the two versions of the cover song playing in synchrony, right? Getting the beats in the same time and stuff like this. You can use these effects to make it work. Okay. Any other questions? All right, well, it's a little bit early, but I guess we'll break for now, and I'll see you on Wednesday.